Well, hi, thanks for watching. I'm going to use this first video here to describe what's called the Law of Universal Gravitation. And it's the foundation for everything pretty much that we do with gravity. And I'll show you in subsequent videos how we can derive other relationships, other equations, and other ideas from this. And I'll give you a little bit of history here. This was actually credited to Isaac Newton for discovering this. And he didn't do it the way, for example, Galileo discovered things about gravity by dropping things and rolling things down a hill and sort of empirically measuring and saying, oh, look what happens. Because Newton couldn't do that. You can't see the effects of gravity on a small scale here on the surface of the Earth without really sophisticated instruments. So he actually used this astronomical data. He was somewhat of a sky watcher, and he would say, well, look at these orbits, and how do we explain this? And then through his sheer brilliance, and especially mathematics, he was able to say, oh, I see what must be happening here. And he actually wrote this in the form of a proportion. So just to give you a graphic of what was discovered, if we have any two masses, and I'm going to distinguish them in size, but they could be the same size, they could be the same kind of object. It doesn't matter what they are. They could be planets. They could be stars. They could be little specks of dust. They could be people. And I'll give one a capital M and one a little m. And what Newton knew was that there are forces being exerted on each of them by the other. So it's what we call an interaction. So the big M is exerting a force on the little m, and the little m exerting a force back on the big M. And they are, by Newton's third law, equal in magnitude and opposite in direction. And how big are these? Well, again, we didn't know an equation when Newton did this. He just knew a proportion. He knew that the size of the force depended on each of these masses and also depended on how separated the centers of those masses were. And here's how we wrote it. The gravitational force is proportional to, there's a symbol you might not see very often, is proportional to the product of the two masses and inversely proportional to the square of the separation distance. Now we've seen, and maybe you've studied other laws where there's inverse square relationships, and this is just another example of that. So that means if we change either of these masses, that the force will change in a direct kind of relationship. And if we change the separation distance, that it will change inversely with the square of that. Now, to turn this into an equation, we need what's called the proportionality constant. And that was provided by Cavendish years later. And so now we write this as an equation with this proportionality constant we call the universal gravitation constant, big G. You got to be careful to use big G and not little g, because we've reserved little g for other gravity numbers, and I'll show you the connection here soon. So big G has a value, and again, this is a universal constant, so it doesn't matter where you are, whether on the surface of the Earth or in the farthest reaches of the universe. This value will be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And if you look at that tiny little exponent there, it gives you a feel for just how small the effects of gravity are. So if we were to take a couple of kilograms in the classroom and put them a meter apart, we're going to get this many newtons of force. Certainly not something we could measure. But if we start talking about huge things like stars and planets and moons, then we can start to see significant effects from these forces, because that's what governs the motion of all these. I'll show you in subsequent videos that we can derive the orbit equations starting with this. So that's the law of universal gravitation. And let me show you one nice application of this. And that would be to find a measure of little g, what we call the acceleration due to gravity, or sometimes called the strength of the gravitational field. I'm going to draw a little diagram here. So this will be the Earth. And here's you standing on the surface of the Earth, greatly magnified, obviously. So the law of universal gravitation says that the number of newtons pulling you and the Earth towards each other should be able to be found this way. Big G times the mass of the Earth times the mass of you. I'm going to use a lowercase m for you because you're so much smaller. and the separation between your centers, which is effectively the radius of the Earth, and that gets squared. So that's how we would calculate the number of newtons. But we've already had an equation that you've probably been using in other earlier parts of this study, and that is that the number of newtons, we usually call it F sub g, and maybe a few weeks ago if I said, well, what is F sub g? You would say, well, it's just your mass times little g, the strength of the gravitational field, which on the surface of the Earth is 9.8. Now, students tend to think that little g is like a constant, and it's not really a constant. It does depend where in the universe you are. If you're on the surface of the Earth, then it's 9.8 or so. But if you're on other planets or moons or anywhere else in the universe, it's going to depend on where you are in relation to what's causing the gravitational field that you're in. So if we just take this and do a little math by canceling those out, then we have an expression here that shows how we get 9.8 for the surface of the Earth. And I'm not going to show this calculation, but trust me, if you put in the mass of the Earth, which you could look up, and the Earth's radius squared, you will get right around 9.8. This also gives you a way of doing this for other planets. So you could change this to Venus, the mass of Venus and the radius of Venus. You could even say, okay, what if I go up here a little farther from the surface of the Earth? Now the separation between you is more than the radius of the Earth. We'll just put in that higher value there, and you will get a lower value of little g for that location. So it's a nice connection between big G and little g. Final thing I want to say, and this is just a word of caution on avoiding the term gravity now, because gravity is a very nebulous term. I want to show you that now we've seen 3 different measures that students all want to call these gravity, but you need to be more specific. This is called the acceleration due to gravity. It's measured in acceleration units. It may also be called the strength of the gravitational field. So this would either be in meters per second squared for something that's accelerating, or more commonly now we'll be using newtons per kilogram, because it gives you a measure of how much force each kilogram of mass will have because of being in a gravitational field. And now we've introduced big G with units of Newton meters squared per kilogram squared. That indeed is a universal constant. This is never going to be anything different than 6.67 times 10 to the minus 11. And then the force of gravity. Of course, this is a force in newtons. It's going to depend on what 2 objects you have exerting forces on each other. So it certainly isn't going to be the same number all the time. So again, just avoid saying the ambiguous term gravity and be specific as to what you mean so that there's no confusion. So there's a nice little start with universal gravitation, seeing how we derive the little g equation from that, and I promise there's more to come. So check back here and stay tuned. Thanks for watching.